the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 82, where today we are going to be talking about the experiments that changed the history of physics.
This is our second episode.
Yeah, I was just going to say, it might sound like deja vu because this is our second episode on this particular topic, kind of like a part two. I don't know if it's named the same way, probably something different, but just again, talking about, the glorious, all the physics we have today, well, is because of a lot of these experiments that took place in these days. So because of a lot of what we're going to be talking about today and what we talk about generally in this type of series is, well, things that literally reshaped our understanding of science or added to it, right? So that's basically today.
And I want to do, after the news, I want to do, a little intro about experimental physics.
Okay.
I just thought about
I would like that.
something I wanted to say.
Sure.
Yes. Quick little thing about this episode.
Yeah.
First of all, this is coming out on Tuesday, not Monday. This is because right now it's Monday, 11 p.m. on Monday.
Okay.
And
Thanksgiving is a big reason.
No, that is the reason.
And Thanksgiving is the reason.
Yeah, Thanksgiving happened. We were both really busy with, being with our families and also having a lot of work to do.
Literally, next week is our midterm week.
Yeah.
So, that's all I can say. That's a lot of work.
We've got a lot of work.
A lot of work to do.
This episode might be a little bit shorter. It might not be. We'll just see where it goes.
We'll see where it goes. But again, as you very rightfully said, it is 11 p.m. on a Monday night. So it's not a primal time to record.
We've got classes tomorrow morning.
Yeah,
and,
we do.
But we're doing it still. So
we're going to make do.
Let's, first piece of news that I want to say.
Big news. Okay, well, you want to say something?
What are you going to say first?
Big news. We hit 250,000.
250,000 downloads.
250,000 downloads. I teased it heavily on the last one because we were at 253 or something. Basically at 250. I mean, sorry. So what am I saying? Like 248 or something, really close to it. And finally this week we surpassed the 250. So that was really cool.
That was awesome.
Very, very excited for it. I mean, thank you to all of you who are continuing to be honest, if it wasn't for you, would we be up here right now?
Wow, that is the most cliche thing you've ever said.
I know.
And yes, we would.
I have to. But you know what I mean, though. You know what I mean. Thank you to all the listeners. Continue to download. If you are a listener, hop onto YouTube. Maybe check out the video as well. But yeah, if you're those, podcasters, then
and we're coming at you live from 3 different angles.
3 different angles now.
My.
Yeah. We got a whole setup going. So definitely go check out the YouTube video because we are putting a lot more effort into it right now, especially than we were before with the whole setup. So yeah, definitely go check it out. And that'll be that. That's the news for the followers, stuff like that. I don't think there's any more news.
I mean, right now we're at 15,740 something followers on Spotify. Still going up.
Still going up.
So that's good news. All right, moving on. For our book giveaway for World Scientific, we're not going to do it today. We are still going to pick comments from last week's episode
Beautiful comments,
as the winner. Thank you to everybody for all the comments,
to everyone.
by the way.
Wow.
But not this week because complications. What's that word?
Complications is enough.
Yeah, sure.
Complications is enough. Yeah, that's good enough.
But yeah, we're gonna pick a comment from the people who commented during this period of time, so don't worry about that. But just a little reminder to everybody: the book that we are giving away, technically last week, is called Adventures in Quantum Land. Subtitle: Exploring Our Unseen Reality, and this book is by Ruth E. Kastner. Yeah, you can go check it out on worldscientific.com. We actually have a discount code for you guys if you want to go buy some books or articles or journals or anything scientific publication related. They have a lot of interesting stuff. And that discount code is going to be in the description, or you can memorize it. It's podcast WS25. So there you go. It'll be in the description.
There it is. Yeah, this is going to be in the description, so don't worry about that. And don't worry about which episode you want to comment on. Like if, let's say, you're hearing it for the first time, oh, maybe I want the book, and you're hearing this episode, you can comment on this one too. And we'll just...
we just said we'll take it from the other one.
No, we'll take it from the other one too.
Okay.
But we can also take it from this one, is what I'm saying. Sure. So if we do see a lot of influx of comments on this episode too, then we'll just do a random comment picker on one of them. And... a random number generator 1 and 2, and then we'll just pick it, like that. Okay, so the whole thing is also we were planning to do it on a nice Instagram live, like we do those relatively often nowadays, I guess, not too much, but we're starting them. So maybe next Friday or Saturday before we record the podcast, we can go on live, and then maybe we can do it in front of you guys.
Yes.
Something like that.
All right. Maybe finally.
Before we get into it. Yep.
The comment of the week, everybody. Make sure to leave a comment if you want to be comment of the week, because we like comments.
Yes, sir.
This week's comment is from Yasmin Ross. They say, "Hi, I'm a high school student from Russia, and I started listening to the Math and Physics podcast this summer. I always wanted to be a lawyer, but your podcast made me fall in love with astronomy and physics. So now
to physics.
Now I am intensely studying physics. Thank you so much for your amazing work. Thank you for your comment. And if you want to be comment of the week next week, leave a comment in the YouTube comment section of this week's video. Let's get into the podcast.
Let's get into it. So you had a little thing on experimental physics.
Experimental physics.
Let's get into it.
So I'm currently taking 2 experimental physics courses right now. One of them is astrophysics related, and one of them is just physics. Ray had the pleasure of taking that course last year, and there's a certain appreciation that you gain from doing experimental physics.
I'm so happy you're saying this, because I think your mindset has changed
a little bit,
for the better.
I think. I'm so happy. Because anytime you do anything in physics, put yourself back, as we do in every single episode, put yourself back in the 1600s right now, and you're discovering equations of motion.
That's
great. You're trying to put the puzzle pieces together, and you want other people to look at your work and say, "Oh, he's onto something. Let me read it. It's well put together. There's some nice
especially
drawings
when people are believing something else, for them to actually move from that and believe you."
Exactly.
It's you really need to show yourself.
And the physicist in question, set up a beautiful experiment, maybe one that we're going to discuss pretty soon, documented all of the equipment he used, exactly all the steps he did, shows his data, his results, and then talks about his results, For the readers, for the scientists that are reading the lab reports and following along and maybe recreating the labs and, then adding on something, discovering something else and writing about that. It's just how science is done. You know what I mean? That's how science is done. You think of something that will give you a result, you produce an experiment, and you just write about it in the most concise and precise way.
Most important part about experimentation is reproducibility, right? About any experiment, you need to be able to, other people need to be able to reproduce it, see the same results, concur the same things.
Quality of the data,
quality of the data is also very important, but reproducibility is one of the top things there, right? So having these, because while I was actually exploring one of today's experiments, I saw this flat earther debunk it.
Oh.
So funny.
Debunked.
It was so funny. It was so funny because, he and one of the major things that he said is that it had never been reproduced, which actually would have been a valid counter argument to any theory, but it had been reproduced multiple times. But anyways, so reproducibility is important. And you know what I mean? It also teaches you that not only does an experiment need to be reproducible, but also you can add things onto it many a times, right? And that's also what we see, especially in the 1600s, where they like some person starts with something and another person 50 years later just adds onto it, takes all the credit. Like, it's sad, but that's what happens because he just finished it, you know?
Oh, that's a shame. That is a shame, actually. All right, so Ray, being the bean that he is, just knocked over his glass of water, so quick break there.
Yeah. Let's just start with the podcast because I think we were going into a little bit of a tangent anyways. Let's just get into the experiments that changed history. So one of the experiments that I would like to start with is the Cavendish Experiment. It's a famous one about calculating the mass of the Earth. So this is in the late 1700s. This is like 1797, 1798. This had been proposed before mid 1700s. And actually had been calculated by, I believe, it was another individual, and it was about 20% from today's value. So it wasn't terrible. So this wasn't the very first one, but this was a very powerful experiment because of what it implicitly deduced. And let me get into that. So the Cavendish Experiment, right? What is it? Well, again, determining the mass of the Earth. The apparatus is, it's quite simple. So Henry Cavendish, hence the name, basically made a hut in this region that was completely surrounded. It could not be affected by any air, any wind. Nothing was really affecting the area inside. And in this hut was the actual apparatus. What was the apparatus? Well, it was quite simple. It was 2 steel balls. Again, I'm not entirely sure, but no. They were lead balls. I'm pretty sure they were lead balls. Anyways, 2 huge lead balls on kind of like a pivoting axis, right? But they were basically stationary. 2 lead balls. Huge guys. On another axis. Now, when I say on an axis, I mean they are connected to each other. So just think of like a center pivoting point, and then there's 2 balls on either side equidistant from that point.
So you mean like an axle?
Yeah, you can think, an axle would be, but it's not exactly an axle because it's not just rods, right? It like holds the ball. Anyways, I mean, you can search up the Cavendish Experiment and you can kind of maybe see what I'm talking about, but it basically just holds 2 lead balls on one side, right? That's kind of like counterbalance. You can think about it. And then there are 2 other balls, much, much, much smaller. I'm not quite certain about the material. It doesn't really matter. But there are 2 smaller balls that also are connected on an axle that are basically close to one of them. So, anyways,
and both the axles are connected to the big
one?
one?
So there are 4. So it's like a spoke.
Yeah,
I don't know if I'm explaining this too well, but it's like a spoke basically where there's 1 axle, 2 lead balls on either side, another axle, 2 much smaller balls on the other side, and they're all connected to this torsion string. They're basically connected on top to a string. So if you think about it, they're like kind of like rotating.
Okay. Yeah.
The steel balls are fixed. For now, the lead balls are fixed. The big guys are fixed. So the only one that can rotate is one of the axles, the axle that contains the smaller balls. Following so far? Really simple. Now, what he does is cool. It requires a little bit of time and a little bit of patience, and because you do have to put it set it up in a particular way. But if you place, and this is actually being done on like YouTube, and many people have been able to reproduce this in their garage. And if you place this axle at a certain angle, this is where it gets crazy. The gravitational force exerted by the bigger ball, it will move the small ball more than the small will move the big. That's obvious. So the big ball, the gravitational force it is exerting on the smaller ball, remember it's on both sides, right? So it's being attracted on both sides. So it kind of moves that axle just a little bit. You know what I mean? So basically
With that much mass?
Yeah.
Just that much mass and it moves the whole thing?
The idea is to keep it at a distance where the gravitational, just hear me out. I'm talking about angles that are like 0.0001 difference, 1 degree difference, right?
Okay.
I'm talking about very small real changes. So what's actually happening is when the force of gravity is...
Oh, you explained this so bad. The setup.
It's 2 axles.
No, I thought...
It's literally 2 axles,
I know,
and then
but
there's a
I
string
thought,
in the
I thought
center.
they were connected on either side of the string.
What do you mean? No, it's like okay, again, it's like you can think of it like a fan. It's literally, just think about it like a fan. On one axle of the fan, there are 2 lead balls, huge lead balls. On another axle that's free to move, there are 2 steel balls.
Yeah.
Again, this is taking way too long for just to explain the apparatus. I'm sorry.
Keep going.
So the idea is basically there is a force of gravity being exerted between the large ball and the small ball at all times.
That's almost unbelievable.
Just listen to the experiment.
No, go ahead.
Just listen to the experiment. So, what happens is there's always a force of gravity attracting the ball, right? So when you place the ball at a certain distance, the force of gravity gets large enough to actually move it a little bit. Now, this is where the interesting thing happens. The moment it moves, remember, this is a torsion, it's a string, right? So the moment it moves, there's now a little bit of a torque force that's experienced on the top. So simply because of the laws of physics, it now wants to come back to equilibrium, right? The more it gets stretched, the higher the torque. So when the torque force is equal to the gravitational force, following me so far? When the torque force is exactly equal to the gravitational force, it will come back to equilibrium. But simply because of inertia, it will continue from equilibrium, and it'll then oscillate like a harmonic oscillator.
Okay.
That's basically that is the experiment. So what does this do? What does this do? This whole time, at the torsion string on the top, there's a mirror through which Cavendish measures the change in the angle of incident light. So he positions himself in a certain place far away from this experiment as to him not affecting with it. It's like far away from it. It's basically in a abandoned completely. There's nothing else there. That's why he was so intent about this in the first place. He positioned himself in a place where incident light always kind of reflected into his big enough region. And whenever this experiment was performed, when he placed these balls, again, I'm not too certain about the exactness of what he did. I just know how the experiment works. So when he probably set this up and went to sit down, again, it's just oscillating literally forever simply because of, or not forever, drag, friction always takes it down. But the initial oscillations, the beauty of that is that the exact amount that it's oscillating, because you can calculate the torque force, right? Because remember what I said in the beginning. This torque force is exactly equal to the force of gravity that the ball is pulling it with.
Yeah.
Right. So what he's basically found is an exact equation for the force of gravity between these two masses without needing the constant G whatsoever.
That's so unbelievable.
It's crazy. But here, it's not even over. I think that was really loud. But it's not even over. This was just finding Fg without G, the gravitational constant. But his actual goal for the experiment was to find the mass of the Earth. He knows the mass of the small ball. He knows the mass of the big ball. He also knows the mass of... he doesn't know... he's trying to find the mass of the Earth. But so what he does is he compares them because he knows the force of gravity between these two balls. And he knows the force of gravity between the Earth and the small ball. That's just the weight of the ball, right? And if he can compare them with a proportionality statement, boom, bada boom, bada bing.
What does that have to do with the Earth, though?
You get the mass of the Earth.
No, but does he set up this the Earth as one ball?
No.
What does
there's a steel. So there again, this setup is still the same way.
Okay.
The smaller ball, he knows the force of gravity between the small ball and the Earth. That's just the weight of the ball. He also now just calculated the force of gravity between the small ball and this massive ball. So by comparing the masses and by comparing the forces of gravities, He deduced the mass. Yes, there it is. I was waiting for this moment. He deduced the mass of the Earth.
That's crazy.
That is crazy.
No, that's crazy.
But here's now. What's crazy is that it's not even over yet.
What?
Because literally after he died, 75 years later, scientists recreated this experiment and were like, God damn, this guy missed a crazy crucial part, calculating G.
Yeah.
Right?
The proportionality.
Exactly. Again, by the way, yeah, so G is the the F equals GMM over R squared, the gravitational constant from Newtonian gravity, which was, because remember, when Newton invented this equation, G was just a proportionality constant. It wasn't a number that they knew. They knew the units for it because obviously they knew what it had to equate to, but it wasn't actually a number that they had any idea about because they just wanted to understand the relationship between these variables. They didn't really care about the values. But then, Henry Cavendish comes up and says, well, I want to actually know the value. So anyways, I mean, he didn't, again, do the G part. He did the mass of the Earth through which he calculated the density of the Earth. And he was like 1% close to the actual value. So he was crazy good. But
which is still like the actual value isn't the actual value.
Again, yeah, it's
because
still like
it's still an
it still has
experiment.
it still does. It still does. And this is also in like early 1700s.
Yeah, so it's like current value.
1700. So it's insane. But again, the 75 years later, they recreated this experiment. Literally, there's no mention of G in the whole paper, in whole Henry Cavendish's experiment about this paper. No goal that was not even a part of it. But an interesting thing about knowing the mass of the Earth is you can calculate small g, like the gravitational acceleration. Now, a thing about the gravitational acceleration is it's also related to the gravitational constant. And through that, there's basically a relationship of the gravitational constant to this whole experimental setup. And they found G basically using that. So
that's a fun experiment.
That was Cavendish's experiment.
That's crazy.
Again, I hopefully described the apparatus to you properly. Again, if it didn't make sense, you can always pull up a Google page and immediately see what I'm talking about. But that's basically the experiment. And it was massive at the time, of course, because the mass of the Earth had never really been known to that level. And also what he had shown was that, the force of gravity does not necessarily have one way to be. Like, you don't need, you can calculate the number without actually needing the theory. You can perform, which is something that he did, which was really cool. So that was Cavendish's experiment for it.
Here's an experiment that's also related to the Earth.
The Earth. Let's hear it.
Because, back in the day, the Earth was mysterious, I guess. Yeah. Or the properties of the Earth were kind of mysterious. Imagine being, like 70,000 years ago. You think the Earth is just, it's like Minecraft. It just keeps going.
Yeah, no, there's not really much there.
If you keep walking in one direction, you'll get to a different biome or whatever. And it'll just look different. But you don't know what the actual thing looks like.
Yeah.
Anyways, scientists, this was in Paris, by the way, in the 1850s. The scientist's name is Fuco.
Ooh.
All right. This is his last name. Anyways, the experiment has to do with the rotation of the Earth.
Okay.
So think about this. People have known that the Earth is a ball since a while now, okay, for thousands of years. And
debatable.
So we now know at this point that orbits are elliptical and all this stuff. But people aren't really thinking about the rotation of the Earth. You know what I mean? Like the common folk. Mm-hmm. Just the scientists are thinking about these things. Yep. But, people who are just living in the 1800s, they light candles and stuff. What else are you doing back then?
Yeah.
That was a joke, by the way. Anyways, what was cool about this experiment is that people got to see physics work or see the world work in front of their eyes. So here's what he did. This is called Foucault's pendulum. What he did is that in the middle of this nice building, it's called the Pantheon in Paris. He set up this 220-foot pendulum with a giant ball at the bottom. It's a 62-pound ball.
Jeez.
Right? So this is a huge pendulum. And on the ground below the pendulum, there's like a circle marked with degrees. And what he did, this is an easy experiment. He just let the pendulum rock back and forth. And throughout the day, the angle that the pendulum was making was changing. And people would stare at it and be like, wow, what's causing it to change? And they realized that the pendulum isn't moving. It's the earth that's moving under the pendulum. And that's what's causing the
pendulum to look like
the illusion of rotation. And so this is a simple experiment, but this was in a public space. And so people were just able to come in and observe the rotation of the earth in front of their own eyes.
That's so cool.
Yeah.
That's so cool. But did he actually like do anything quantitative? Like through this angle?
I mean, not really, because the period of a day is a day.
No, but I know. But I thought this whole thing was like, oh, he actually calculated something big. That was kind of sad that he. I mean, it's a cool party trick for like why he was, because I mean, at the end of the day, if it is rotating, I mean, which it is, he was proving that it rotates.
Well, actually,
or did he calculate like some sort of speed?
There is some sort of calculation involved that you can do. So essentially, this has to do with your latitude, because if you are on the equator.
Oh yeah, of course, yeah.
If you're on the equator,
you're moving fast.
It's not ever gonna.
Yeah, of course.
It's not ever gonna change. And if you're in the North Pole, then it's directly gonna do one rotation every 24 hours. But depending on your angle, it changes the actual period of the rotation of the pendulum. In Paris, it actually did an entire clockwise rotation every 30 hours because of the latitude angle. It would slow it down, right? 'Cause the fastest you can go is 24 hours. And then when you go down, it goes to 0 and then back to 24 hours, but counterclockwise. So negative 24 hours if you want to think about it that way.
So what were like the big lessons from that? So the earth rotates.
Well, one, the earth rotates. And two, it confirms predictions of the earth being round.
Were pendulums a thing before that?
Of course.
Okay.
1850?
Okay. Oh, 1850, of course. Newton's pendulum, of course. Okay, no, of course. So was he verifying something? Okay, maybe he was just showing.
Also, speaking of pendulums real quick, Galileo, when he was a little boy.
Oh yeah, that's famous. Yeah.
Yeah, this is a famous one. But just real quick, when he was in church and he was bored, he actually measured the period of a chandelier that was moving back and forth with his pulse. And what he noticed was that if the chandelier was had a high angle of oscillation, or if it had a low angle of oscillation, the period would be the exact same. And so what he actually discovered something that you can do mathematically with, simple harmonic motion. You find that the period of a pendulum only depends on the length of the rope or whatever you're using, and not the mass nor the angle, the highest angle at which it rotates.
That's pretty powerful though. Like that's not counter, it's not intuitive at all. Like that's not dependent on the mass.
You would think that the mass, it has a big mass, and so it's slower. It
actually
moves
no.
slower.
Like if big mass would be moving.
No, I think small mass, and then it'd be like, big mass, it would move slowly.
Whatever. Anyway, this is just intuition, but clearly it was wrong because it only depends on L and G. Yeah, that's basically it, and that's pretty cool. That's a cool little rotational Earth. No, the Galileo thing is definitely very cool. That guy was a. We need to do him on a history of physics.
Yeah.
Oh my God, Galileo would be insane.
Yeah.
We have so many. Anyways, let's continue. Unless you have anything else.
No, that's it.
Let's continue. On to another very famous experiment. James Prescott Joule. Yeah.
Yep.
Basically, the inventor of the Joule, right?
Oh.
Or at
Which
least it was
one?
named after him. Most of most of it is. But what happened was in this particular experiment, he actually did two things. So it's called a paddle wheel experiment, where he proved, number one, basically the first law of thermodynamics. Kind of came up with it, where work and heat are related. And then he came up with the same experiment, also kind of proving conservation of energy. So crazy guy, crazy stuff with energy. I mean, that's just Joule, obviously. I mean, you hear his whole thing, and it's all based on energy. So what was this experiment? Again, all these apparatuses, they're not the easiest things to explain, especially on a podcast, right? I mean, I will try my best. I think we should do, like, if we're talking about these kind of things, maybe put like a picture while we're talking. We'll figure it out in post. But maybe we're gonna change that up, make it a little bit nicer for at least the viewers out there. So yeah. So what this experiment is, it basically was two masses hanging on either side of this barrel of water. In this barrel, there were paddles spaced equally from one another. There were three sets of paddles, again, kind of like rotating almost, paddles rotating. And they were influenced directly by the movement of the masses. So it was kind of like connected to a pulley almost. And if the masses moved down, the paddles would rotate. If it moved up, the paddles would rotate, whatever. Yeah. Paddles would basically just rotate, and the energy would be transferred.
So they were kind of like on a string, and the string would make it turn.
So exactly. So you would like kind of like turn the string, or like technically
like a gyroscope, you know how it, like,
the idea is to put the masses on to move the masses to some height and then drop them. And then as they're dropping, the paddle wheel inside the water
spins.
It starts to churn. Now here's the interesting thing about this experiment. In this barrel of water, number one, it's completely sealed shut, and number two, there's a thermometer that is currently measuring the temperature of this water. And what it notices, and I think we know where this is going now, what it notices is as the paddle wheel spins more and more, the temperature of the water increases.
That's also insane, though. Like, if you think about it.
Like, how do you even... That's crazy.
No, but the fact that it goes up by a measurable amount.
Oh, yeah?
Yeah, like, think about just, like, spinning water with your hand and, like, the temperature.
No, but obviously this was,
going.
like, massive. These were massive blocks that were still moving this whole thing. Okay. Because at the end of... Because what he ended up doing is because, remember, he knows the masses of these things, so he can calculate the potential energy. He knows the energy that should go into it. And what he found out was basically that the amount of energy, like the higher that he dropped it from, the temperature would increase directly proportionally to, the energy. So he basically made a relationship between work and heat.
Is it 3/2 kBT? Is that the linear?
Yes, right? That's Q. No, yeah.
I thought that's kinetic energy or something, like, or whatever.
Because the whole what actually is happening in this whole experiment is your potential energy it's getting converted to kinetic energy,
and then that gets converted to thermal.
Exactly, and that is getting converted to thermal energy in the water. But technically, kinetic energy is first going into rotational energy for rotating these paddles.
That's the same thing, though.
Which is then going into thermal. But yeah, if you think about it, but it's again because why? Because temperature is dependent on the speed of the molecules in the water. So paddle is increasing that, and that's how it increases for those that were wondering about that connection. But that kind of proves that, hey, work and heat are related. And again, the cooler thing about this as well is conservation of energy, is that he found out that the water heat, number one, also estimated the specific heat of water. So he got a number relatively close to, 4 point something. Like
I don't remember.
Kilojoules per meter cube. It's whatever. He got a relatively close number to that. He actually
specific heat is joules per mass. No, you divide by the mass.
That's what I said.
You said meter cube.
Oh, kilogram cube. Sorry.
No, kilogram.
Oh, sorry, not cube. Kilogram per kilogram. Yes, you're right. And there was 1 kilogram of water, and he basically put in this much because he literally tested out 1 kilogram of water, I believe, and seeing, or maybe a proportional number, and seeing the amount of temperature increase, right? So through that relationship, he was, number one, able to estimate that, hey, work directly affects heat. That means heat and energy are connected. Now, again, this is like obvious, but it wasn't. It wasn't then at all, you know? So it was a very big... Oh, yeah, exactly, that's what I'm saying. Okay, yeah, so it's not... That's a little different equation. The MCAT equation, the Q equals MCAT equation for the thermodynamic freaks out there. But yeah, Q and T are basically connected through an equation. And again, he basically introduced the first law of thermodynamics that, hey, these things are connected in the first place. And... continuing on conservation of energy. I mean, his name is Joule. Like, if he didn't do anything in this, what did he do? Right? So anyway, this was one of his really cool things, the paddle wheel experiment. And I mean, rightly named. So again, all these things were relatively large. Like, all of them were very, very big. Like, this pendulum clearly was like 20 something feet. Like, what? 200 something. That's crazy, man. That's insanely huge. And, all of these things, I mean, even the Cavendish was in a house. This also in a relatively large space. So all these experiments, especially back then, because it's just easier to look at, it's easier to do, easier to construct than making these microscopic things, right? That we can do now in labs. So again, something really cool that he was able to do in his time.
So let's bring it down to the atomic scale for a second.
I don't know if I said, but this happened like in the 1850s. I don't know if I mentioned that, but
So
like somewhere around like the mid 1800s is where that particular experiment took place. Okay, let's go into the world of the quantum. Let's start.
The atomic scale, one of the most beautiful scales that exists.
Question.
May I add? This was, of course, very timely. 1897. Okay. Actually, the experiment I'm talking about is in 1909, but in 1897, this is when the physicist J.J. Thompson described. Did we talk about Thompson?
No.
Okay. Anyways,
but I didn't even know which one you were talking about until you said, yeah.
So he discovered electrons negatively charged. Okay. Now, over 10 years later, Millikan and his partner.
They never remember the partner.
They wanted to they wanted to figure out the exact charge of an electron. Before their time, the only thing was known was that electrons are negatively charged particles. But the most difficult thing about the atomic scale is that it's so small and it's so difficult to actually come up with experiments that can give you data about these tiny, tiny particles. And one thing I remember, I was talking to a friend about this. I said, imagine you try to calculate the position of an atom. It doesn't matter how you go about finding the position, but for the position of the atom or the electron or whatever to be registered in your head, to be like, oh, there it is, it needs to be like on a screen or something. But just know that the pixel that tells you the electron is here, that pixel is made up of billions of atoms. So it, like, put that into perspective. You want to measure the position of one particle. For you to even know that, to know that position, you need billions of atoms. So
it's crazy,
like,
man.
Atomic
scale is definitely it's a whole. It's a whole episode. We could go a whole episode on the atomic scale.
That's actually a good idea.
That's a really cool idea you just came up with. But that's
So what did they do? This is actually a pretty crazy experiment.
Robert Millikan, right?
Yeah.
Wasn't it? Yeah.
So this is absolutely crazy. So what they had is like this barrel, I guess. And in the top of the barrel there's an atomizer, which is like, you know, like perfume bottles. They mist. They had an atomizer, and what they did is they put oil in the atomizer, and they would mist the oil into this barrel, and the oil would just fall down. And then somewhere along the lines of the particles falling down, there would be a negatively charged plate with holes so the particles can fall into the holes, right? And then at the bottom of the barrel, there was a positively charged plate. And then these two plates were connected to a battery so you can control the actual voltage or the difference in electric potential energy. What would happen is that some of these particles would lose electrons. Now, Rehan, what happens when something loses electrons?
It becomes positively
charged. That's right. It becomes positively charged. And so, one more detail. They had a microscope that was located in between the two plates so that they can see stuff that's going on. And so what they would do is they would adjust the voltage between the plates so that the force of gravity pulling the oil droplets down would be counterbalanced by the electric force repelling the positively charged oil droplets upwards. So you had a positively charged plate at the bottom, right? So that you get a counterbalance of the forces. Now, if you look through the microscope, you would see droplets, and they're just suspended in midair. They knew why they were suspended, because they were missing electrons and that they were being repelled. And there you go. Now, next thing you know, I don't know exactly the details of how they were able to measure the masses of the droplets.
Oh, okay.
But they were able to. I think it's based on the size.
Sounds like it will help.
Based on the size of the droplets, they were probably like perfect spheres. You know what I mean? Because they were suspended. So they were able to figure out the mass. It definitely had something to do with, like the radius of the droplets. From there, you can calculate the volume and then connect that to the density of water. Anyways, they were able to do it. And then what they would do by changing the voltage on the battery, they would see that, okay, some droplets are suspended when it's at a certain voltage. They would mark down the mass of the droplet and then the voltage connected to it. And then they would do this for many different droplets and get a list. And here's what they would see. They would see that, well, obviously you connect they know that the force of gravity is equal to the electric force because there's no force acting on the particles. And they know the electric force. They know the equation for it. You need a charge. And so what you did is, you know the force of gravity, of course. You would isolate for the charge. You'd isolate for the charge of each particle. And they would see that the charges that they would solve for were integer multiples of something. Rehan.
No, well, what?
Rehan, as you know, we know this now.
Yeah.
But the charge of an electron is 1.602 times 10 to the minus 19 joules. The results that Millikan and his partner got from this experiment was, okay, the charge of this droplet is, 3 times 1.6 times this, 4 times 1.6.
So they got this constant.
10 times. Well, every single result was an integer multiple of this something. Charge. So what was their conclusion, Rehan?
Oh my. That the electrons were charged.
No, had a charge
or
of
had a charge.
1.6.
Yeah.
They figured out the charge.
Yeah, they had the charge.
They figured out this charge. They said you can't go below this charge, and also it is an integer multiple. Every single time it's an integer multiple. Therefore, the unit charge of an electron is minus 1.602 times 10 to the minus 19 joules. And that's how they figured it out.
That's crazy.
No, that is a crazy experiment because, they figured out a way to analyze the atomic scale. Absolutely brilliant.
I mean, again, going into the atomic scale in the first place. Wait, when was this again? Late 18?
This was 1909.
1909. I mean, still, the quantum hadn't really, even till today, we're not really very good. I guess with Large Hadron and everything, we're okay. I guess we're okay with the quantum world. But it's still interesting to see that even, early 1900s. Because I guess this was kind of Einstein's time. Yeah, 1905 was his crazy year. So I guess quantum mechanics was kind of stepping up into it. So it was kind of getting a little bit bigger.
By the way, his partner was Harvey Fletcher.
At least you mentioned
Putting
him.
it out there.
Name drop. Anything else you want to talk about in the oil experiment?
I think that's all.
I think that's all.
You got one more experiment?
I mean, I could.
No, go ahead.
Because I was just reading up on it a little bit just before, and I just thought it's a very simple, very, very characteristic. Okay, I'll just say it. Newton and splitting up the lights, basically splitting up the colors from the prism. That's like almost like a grade 10 classic. Wait, grade something classic.
Grade 11.
Grade 11 classic, where we learn light has different wavelengths, or at least a part of it. So take yourself to Newton. This guy has had the best year of his life. He's invented gravity. He invented calculus. He did everything. And he's chilling.
People were just floating.
This is just...
before.
I love that joke because it's just... Anyway.
Oh, it's so ridiculous when people think that like the Apple story is true. I
mean, there is a level of truth, though, that is apparently documented.
There
is
a certain level of truth, but imagine an apple falls on his head and he's like, "Oh my God." And then the equation just pops. Like you need to be.
Oh, that's what you mean.
You need to think about these things, like before the apple actually falls on your head.
Yeah, no, for sure. Like, there's no way he just thought about it because of the apple. The apple probably happened.
No, also,
but it wasn't like his primary reason for.
Thing about the apple, he was definitely thinking about gravity before the apple falls on his head, because an apple doesn't just fall on your head and you're like, oh, let me just dedicate my life to calculus and physics and figure out what happens when
because of the apple.
No, he was thinking about these things way before the apple.
Oh no, for sure. No, that's what I'm like. Yeah, no. I mean, obviously, there's so many misconceptions about Newton. Like, oh, he died a virgin. No way. Isaac Newton.
I mean, maybe.
No way.
He was a Catholic.
Isaac Newton.
He was a Catholic.
Isaac Newton.
He was never married.
He was the god of like science. Science was like such a thing back then. I don't know. Again, I'm like 99.9% sure it's a myth, because it was just a thing that was invented. Like, oh, Einstein was bad at math, just to make people feel better, kind of thing.
True.
But that's what I'm saying. He was not.
I mean, he wasn't the best.
He wasn't the best. He actually was not. He needed a lot of help in his general relativity and stuff, and he actually did not do a lot of his own math. Yeah. He actually outsourced it.
But he had the ideas, though.
He had the ideas.
The ideas.
Anyways, we're completely tangent. Let's go back into Newton. So this guy's had an insane year, basically. And people at that time believed colors were a mixture of light and darkness. They didn't really understand.
That is so dumb.
How colored. So mean. What would you think?
I mean,
there's no way.
Really?
There's no way.
Like, it's a mixture of light and dark. Are you serious right now?
And then Newton discovered, well, no. Not exactly.
No, good
true.
For him.
Right. So I mean, he thought about it originally, I believe, when he was like seeing a book at a far distance, and he like noticed that, hey, it wasn't colored at all, but instead it was a little gray because it was very far away. So there was a deduction that he made from that where, ouch, why is my eye is killing me right now? Where he basically went home and said, hey, let's see what happens when I basically look at light through a glass or through a window. And I believe the original time, again, I'm quite uncertain about the exactness of what happened. I mean, no one really knows exactly what happened, but it was something where the light was shining through his window onto a screen. And he noticed that the light was refracting on the bends of the window. I'm assuming something like this, where the sun on the screen appeared a little bit red at the bottom, and it appeared a little bit like light blue on the top. Like, no, actually not, sorry, dark blue on the top. And he was wondering, well, this is a little interesting, right? Like, why am I seeing colors come out of the sun? And then it was his famous prism experiment where he actually used the prism to legitimately split up light. I believe he used two prisms. I believe he actually originally used two prisms that split it up in a certain way where he could see it very clearly. And, well, the big deduction from that, well, hey, color is not a mixture of light and darkness, but it is, in fact, light, right? It's just different versions of light. And obviously a bigger thing that he also deduced from this is that colors, all of the colors make up white light. Because when he originally split it, it was white light that he split. And the original thing from the sun, obviously, wasn't, I don't know if you can characterize that as white, because I guess it's all wavelength, all spectrums and everything. So you can kind of characterize that as light as well. So that was the original, but as obviously the experiment got more defined, it was pure white light that then split into these almost 7 beautiful colors. And again, not the exactness of the experiment, just talking about the importance of it right now. It's just crazy to think about that it's something so obvious today, or at least I don't know if everyone knows it.
Do you think you can fry your corneas if you project this prism light onto your face? But what you do is like you put like red all the way to purple, and then you put UV rays directly into your eyes, because like it wouldn't hurt your eyes. You know what I mean?
Probably not good for yourself.
No, it's not good. That's the point.
Yeah.
That's what I'm saying. Like, do you think like if you split the light, you can concentrate the UV rays? I'm not saying put them into your eyes. I'm saying they're still there.
I mean,
they should be, right?
It's not. Wait, but what do you mean? Because white light is still visible. It's only the visible spectrum. I know,
but there are UV rays in.
Yeah, but light. Not. I mean, yeah. If we're talking about from the sun, yes, of course. But I'm talking about like if it's like a white light flashlight. If I'm talking about like the original thing happened where it was like a sun window, he saw it on a screen. But the actual prism experiment, even if it did take place with the sun, then maybe you're right. Yeah, but then the UV rays would also refract in the same way. But again, something that this proved, number one, is that this light breaks up into these 7 colors. And number 2, well, that light not only does this, but it also goes in a weird angle. Because in this prism or whatever contraption that he had used, it did not obviously go straight, and kind of a proof of refraction too. Why not? Wow. So like there were a lot of things that this experiment kind of sub-proved, but like the color thing is a famous one because it's so radical to think about a time when, well, you clearly laughed at it, when people thought that colors were a mixture of light and dark. Mm-hmm. Or any idea of that where they weren't really thinking about why a color is a certain color. And then this guy comes up with something that today is thought about to be so obvious, but so fundamental in his time. I mean, this guy was just crazy after crazy, man. Imagine like
absolutely insane.
Like, Newton is just on a new level of crazy.
So,
anyways, I think that's basically. Do you have anything else?
No.
Any more experiments that we want to?
If you enjoyed the
good.
experiments that we mentioned today, make sure to leave a comment, leave a like, and also to follow us on Spotify or YouTube or anywhere else you're listening to this.
Mm-hmm. My God, I am so exhausted right now. It is so late at night.
Make sure to do anything else that I missed. And
follow us on Instagram. If you're listening to us wherever you are, why not go follow us there too?
Boom.
Boom.
So, yeah, this has been episode number 82 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.